Hey everyone, we're back. We're talking about topic 7.2, nuclear reactions. And to start that out, we talked a little bit about that last time. To start that out, I want to just kind of reiterate what we went over last time. So let me just put on my little title here. And remember we did this reaction. We did 14,7 nitrogen, and we hit it with this really fast moving alpha particle, which is a helium nucleus, and it transmuted should be an 8, transmuted into an oxygen plus a hydrogen, basically a hydrogen nucleus. And if you add up all of the nucleons at the top, they add up all the protons on the bottom, they both add up, and so we have a balanced equation here. And this was a transmutation. This is what the alchemists were trying to do. They were trying to change lead into gold, and we now have that capability to do that. We understand how that works, and we've actually done it, but it's so extremely expensive to do that it's not really worth doing it. All right, and so then we also have decays. Let's see if you remember what kind of decay this is. We have polonium, and it will decay, because it's so big, doesn't want to stay together. It will just decay into lead and an alpha particle. So can you remember what kind of decay that is? It's really not intuitive. It's an alpha decay because it produced an alpha particle. So that's the kind of decay that it is. So that is just a quick overview of how to do these equations and what they come up with. If we were going to have the test, the IB test, I would say they would ask you something like, what kind of decay is represented here, and they would leave like the alpha particle off, and you'd have to figure out what that was. Or they would say polonium went through alpha decay, what was the resulting nucleus, and then you'd have to come up with a lead nucleus, that kind of thing. But there's an interesting thing about this. We know about the conservation of energy and mass, right? You can neither create nor destroy energy. And when you do chemical equations, you have to make sure you have the same amount of mass on one side of the equation, the reactants, and this is the same for here, we call these reactants, and the products. You have to have the same mass. Well, there's a thing that happens when we're dealing with nuclei. We don't always have the same mass on one side as the other. You go, wait a minute, how does that work? You have to have conservation of mass. You have to have conservation of energy. We may not even have the same energy. As a matter of fact, I guarantee you that no matter what reaction you do here, you will not balance the mass or you will not balance the energy on both sides. So what's going on with that? That is something that we call mass defect. And it's very important, and I'm going to go through this very, very carefully with you, because this is actually very interesting, and it's the reason why there's life on Earth as we know it. Without this kind of thing happening, there would be no life anywhere in the universe. All right, so let's do a nuclear equation. Let's take two hydrogen atoms, their nuclei, and let's bombard them with two neutrons. Now I'm introducing a new one here. The neutron is a 1 and 0. Neutron is a nucleon, right? It's in the nucleus like a proton. It's a neutron, so it's a nucleon, but it's not a proton, so we give it a 0. So we got the 1 and the 0. Whenever you see that, even if they have an X here or whatever might be there, it's a neutron. All right, once we combine those together, we get a helium, an alpha particle. All right, so helium. This is basically the process that goes on in the sun. We are fusing hydrogen into helium. And let's see. I think how I want to approach this is, let's talk about some standards first. So we have a thing called the Universal Atomic Mass Unit. Normally it's just called AMU, especially in chemistry it's just AMU, but in physics we make sure we have to call it, we have to be so much more precise than chemists have to be. So we call it Universal AMU. And what that is it's 1/12 the mass of an unbounded carbon atom at rest. Because at these tiny sizes, any kind of velocity, if we study relativity, we'll see that any kind of movement affects the mass. The faster you go, the more mass you have. So if this carbon atom has to be at perfect rest and is not bonded to anything. So 1/12, and that is equal to 1.661 times 10 to the minus 27th kilograms. Now there's another unit that represents kilograms, but it's a little bit different, and that is the equivalent of 931.5 mega electron volts per coulomb squared. Okay, these are two numbers. These two numbers, IB expects you to know. I believe, I can't remember, I don't have my data booklet in front of me. I don't know if these two things are in there or not, but you definitely need to know them to do this kind of work. Okay, so that's the atomic mass. It's very important to understand this, and it's usually the unit that physics uses is just U. Universal atomic mass unit. They just use U. So what I want to do now is I want to create a little bit of a table for you. Particle and its mass in universal AMUs. Okay, so the first one is an electron, and its mass is 0.000548 U. A proton is 1.00727 U. All right, a hydrogen atom should be an electron and a proton, right? It's just a proton. We've got one proton, one nucleon, so no neutrons or anything in there. The mass should be exactly the same. It should be this plus this. And what it is that which turns out, let me see, 1.007825. If you add these together, you do not get 7825. You get 7819. And that is part of this mass defect going on. You don't always get, on either side of the equation, the same mass. And I'm going to get into exactly what's happening with that and why it does not break the laws of conservation of mass and energy. All right, so the next thing we have here is neutron, and it is 1.008665. Notice it's bigger than a hydrogen atom. Pretty cool. And then helium is 4.002603. All right, so these atomic mass units. Now, the reason why I'm writing these down, number one, IB would always give you these things on the test if it was necessary to use them. They would always provide this. You don't have to look at a periodic table for it at all. So I've written them down here, and we're going to compare the mass on this side of the equation, on the reactant side, to the product side, and see what we get. All right, so over here we have 2 hydrogen atoms, so it's 2 times 1.00007825, and 2 neutrons. I'm running out of room here, so 2 times, and we're going to add these together, 2 times 1.008665, and that gives us a total of 4.03298 U. And on this side we have just the helium atom, which is what we want, and its U is 4.002603. And you can see that this one is much smaller than this one. It's not the same. We've lost some mass. Have we lost mass? No. We've actually converted it to something else. And the only thing that's left to convert it to is energy. So that amount of mass has been converted to energy. That's the mass defect. And in this case, the mass defect is 4.002603 minus 4.032980, and that gives us a mass defect of negative 0.0303777 U. All right, universal atomic mass units. All right, so that's the amount of mass that has been converted into energy. All right, so let's figure out how much energy that has been converted into. We have a very nice equation that lets us do this. E equals mc squared. If we know the mass, we know the speed of light. No, in this case, we don't know what the energy is. Mass is 0.00, I'm sorry, 0.30377 U, and speed of light is 3 times 10 to the 8th. All right, so meters per second. All right, so we know that, but however, we need this mass in kilograms. U does not cut it. We need to have it in kilograms. So we need to convert this. Well, good. We have a conversion here. And a U is equal to 1.661 times 10 to the minus 27th kilograms. So we can now convert that. So let me do 0.0303777 U times 1.661 times 10 to the minus 27th kilograms per U, and that equals 5.044 times 10 to the minus 29th kilograms. So out of that mass that was missing, that's been converted, it's 5.044 times 10 to the minus 29th kilograms has been converted to energy. All right, so how much energy is that? Well, we can now plug that into our equation up here, and we get E equals 5.044 times 10 to the minus 29th kilograms times 0.0303777 U. Now, what am I doing? Just totally, my brain just went off on its own there for a minute. So let me erase, obviously that's not the speed of light. All right. 3 times 10 to the 8th squared. And that's going to give us 4.54 times 10 to the minus 12 joules of energy that was released by this reaction. And this is interesting. So I can say up here plus 4.54 times 10 to the minus 12 joules of energy. Okay, so this happens to be a pretty stable arrangement. By releasing this energy, helium wants to stay together. We could reverse this process and introduce, just like enthalpy in chemistry, we could introduce this energy back into helium and make it break apart into these constituent parts. So if that's the case, we call this the binding energy. That is the energy that helium wants to give up so it can stay bound together. And the bigger this number is, the bigger that energy that's released, the more stable the product is, whatever this product might be. We want to, if we want to have a very stable nucleus, we need to release a very large binding energy. Okay, so let me show you a chart here. And sorry, it's not bigger, but this gives you an idea here. And this is binding energy per nucleon. So let me come back here, and what we can do with this, 4.54 times 10 to the minus 12 joules, we can divide it, in this case, by 4, because helium has 4 nucleons, divided by the number of nucleons. And in this case, we get 1.14 times 10 to the minus 12 joules per nucleon. Okay, so that's the binding energy per nucleon of helium. Makes sense. I mean, that's pretty straightforward. Now, if this was some other element here that had 6, we'd divide it by 6 or whatever to get their binding energy. Okay, so looking at this is binding energy per nucleon, and that is how strongly they want to stay together. We see that iron here is actually the most stable element that we have, because it is got the highest binding energy of all the other elements. So when we can put everything together here, put it together, and then when it gets to iron, that's as stable as the elements are ever going to get. From then on, the binding energy gets smaller again. And this on this side has to do with the size of the nucleus, which we've discussed about strong forces versus Coulombic forces. Okay, so that is the binding forces and how we get them. It is how we figure out the mass defect. We take the mass on the product side minus the mass on the reactant side, and that difference is our mass defect. And then we can calculate how much energy has actually been created from that mass defect and what that means for the binding energy, how much binding energy per nucleon there is. Okay, so I want to talk about a couple more things here. We're just about through here, but I want to talk to you about fusion and fission and how that ties into all of this. Okay, So first of all, let's talk about fission. Fission is splitting of larger nuclei, can't spell, larger nuclei into smaller, also known as daughter nuclei. And fusion is combining two small nuclei into a larger nucleus. Okay, so let me give you some examples of this. All right, so fission. Fission is where we basically tear things apart. We take it apart. So in our reactors, we use uranium-235. And we hit that, oops, sorry, don't want to, it's not a decay. We want to hit that with a neutron. And when we hit it with a neutron, it makes uranium-236, which is very unstable compared to uranium-235. Very unstable, and it almost instantly decays, undergoes a decay of, well, basically turning itself into two different other atoms. And one of those atoms is 14054 xenon, and the other one is 9438 strontium, and then it produces two more neutrons. If you add all of this up along here, it would add up to yeah, 235, 236, or 236. Yep. So it all adds up, and so that's what we get. And if you notice, we started out with one neutron floating around, and now we end up with two neutrons floating around. They're not floating. These things are flying out because they are coming out with, because of mass defect, some of the energy goes into kinetic motion for them. All right, so think about this. We have a neutron that comes in and hits a uranium-235, and that ends up producing two more neutrons, right? Oops, get that going the right way. Two more neutrons, and then those hit stuff and they produce neutrons. Can't get my arrows drawn. And then those hit and they produce. You can see that this is an exponential growth of the number of neutrons that are available. This is called a chain reaction. It's exponential growth of the number of neutrons. Exponential, I'm having a hard time spelling right now. Exponential growth of the number of neutrons. And so this would get quickly out of control. This is what happened at Chernobyl and the Japanese nuclear reactor, Yokohama, I think it was, that they got out of control. The chain reactions got out of control, and it just basically was a very controlled, but out of our control nuclear explosion. It was a very slow nuclear explosion, and created radiation everywhere and so forth. And the reason why those happened was they had problems with their control rods. There were many other things were wrong, and things happened, but the control rods failed to do their function or were not used correctly. And a control rod is a very complex thing that is designed to absorb neutrons. as they come flying off of this thing. So you can limit the number of neutrons that are hitting other uranium nuclei by using these control rods to absorb them. And if you use all your control rods, you completely stop the reaction. If you lift them completely out and they're not there at all, you have this runaway chain reaction. And that's how they control how much energy they're producing in a nuclear reactor, is by moving these control rods around. Okay, so that is fission, and that's what we do to produce energy using nuclear reactors. Is we do fission. We break things apart, because it's actually kind of easier, not kind of, it's a lot easier to break things apart than put them together, as happens in fusion. Okay, so another way of looking at what happens on the sun. It's actually a very complex process, and there's many equations that can accurately represent it. But here is the most accurate, I guess, the best one, the best describes what's going on. All right, and plus energy. That the photon can also be representative of energy. So you notice the two hydrogen atoms here. One is deuterium, one is tritium. These are highly abundant on the moon. That's why there's kind of getting to be another race to get to the moon. Part of the reason is we want to get some of this stuff, because there isn't this much stuff. There isn't much deuterium and tritium here on Earth. It takes a long time to synthesize it. These combine and they form a helium atom. They give off a neutron, and lots of energy through this process. This is the reason why there's life on Earth. That energy that comes from the sun. The sun is 93 million miles away, and on a Texas summer day, it's so hot from 93 million miles away that we just want to stay in with the air conditioner. Feel like we're melting. You can't walk on asphalt because it's so hot. So it's a lot of energy getting produced from this reaction. Now, the problem is, to do this kind of reaction, you need a lot of pressure and you need a lot of heat. And so only in the core of a star does this exist at this time. So we haven't really been able to do it. We can do a very, I guess you call it a flash fusion, that lasts for millionths of a second and produces a lot of energy. But we can't sustain it. We just can't do it. So come back here and looking at this chart. Fission, where we tear things apart, this is where things want to be torn apart to get to their stable element, and they release energy to do that. So after lead, everything wants to fall apart, and that's basically because the nuclei are so big. On here, on the other side of iron, I said lead, didn't I? On the other side of iron, everything wants to be put together to release that energy. They want to be bigger. They want to bind together. That strong nuclear force wants to be used and give up energy so that things can stay bound together. And so iron is the dividing line right there. The interesting thing, let's go to astronomy on this, because this is the key to the universe in a sense. In a star like the sun, it is right now fusing hydrogen into helium in the core. It's doing 700 tons of hydrogen and fusing it into 695 tons of helium every second. Every second. And we'll do that for the next 4 or 5 billion years. There's that much material up there. And it may, at some point, it'll start fusing helium into lithium and oxygen and things like that. But it will never have enough material to get all the way up to iron. Now, there are stars that can fuse. They'll go from hydrogen to helium, and then the helium will start fusing into lithium and oxygen into carbon and things like that. I might have said that backwards. But eventually, it will start producing iron. It will push two two atoms together and fuse them together into iron. And the interesting thing is, the instant a star does that, I mean that second, that split second that it produces that iron, it dies. It actually goes supernova, because that iron is so stable, it does not want to fuse into anything else. It takes energy to force it to fuse into something else, and that energy is from the fusions that have gone on before, you know, the nuclear fusions getting up to iron. All that energy is immediately taken by the iron atom to fuse into something else, and the fusion process stops. Once the fusion process stops, due to lots of mechanics that I don't want to go into here, the star explodes. Sun will never do that. Sun will never explode. But these big stars that can fuse iron, boom, they'll explode, because iron does not want to be anything else but iron. Everything else wants to be iron. Iron is it. So that is nuclear reactions. And we covered mass defect and that energy that is produced by these reactions, where mass is converted into energy, so that the energy and the mass on one side of the equation do not equal the mass and energy on the other. However, that difference is because the mass or the energy was converted into something else, into either mass or energy. And so the laws of conservation of mass and energy are conserved. And then we talked about the binding energy. That is the binding energy, and we looked at per nucleon and figured out that iron is where everything wants to be. And that is the heart of nuclear reactions. It's the heart of why we have nuclear reactors that can produce a lot of energy. And it's the heart of why the sun and other stars are producing all of the elements that they are. So with that, there are worksheets that go along with this that are attached. So work those. And again, if you have any questions, you just let me know, and I'll be glad to help you answer. Claire?
Yeah.
Were you getting bored?
Yeah.
Did you understand it at all?
No.
I thought you might.
The only thing I understood was that I don't know anything.
That's funny.